Okay, this is 2.5, simplifying rational expressions. This is the beginning of the new grade 11 stuff. So we actually start to talk about fractions. And so the main purpose of this is to actually understand like what a rational expression is. And so what we're going to be doing is actually in this lesson is simplifying fractions. We're going to be reducing fractions to lowest terms. Now you're going to be doing it in the grade 11 way. Like we're not going to be reducing number fractions to lowest terms. We're going to be reducing algebra fractions to lowest terms. So in Learning Target 6, students will be able to simplify rational expressions by using the same rules that apply to numbers and state restrictions caused by the denominator. And so we'll spend some time talking about restrictions. So we ask, are the following equivalent? F of x equals 2x squared plus 2x over x, and g of x equals 2x plus 2. Now remember, like, to determine if something's equivalent, like, you actually have to determine that it's the same for every value of x. So it's actually easier if they're not equivalent to just find one number that makes them not equivalent. And so we actually notice that, like, you guys can pause it if you want to take some more time to look at this. We actually notice after we sub some numbers in that almost every number will work the same way. And so we actually see that and I just did this in Desmos, create a little table of values, but every number you're actually getting the same thing. But the problem becomes that when x equals 0, this first one is actually undefined. Now, if you think about why, it's just because if you sub in 0 here, you've got 2, but like if you sub in 0 here, on the top you get 0, and on the bottom you actually get 0. Now the problem isn't with the top being 0, the problem is with the bottom being 0. You cannot divide by 0, not ever. It doesn't make sense, and like that's actually when math is undefined. Think about like division as a way to divide by a certain amount of people or divide by a certain amount of objects. If you have nothing, if you have no one to divide a chocolate bar by, it just doesn't make sense. It's called undefined. And so if you sub in any number for both x and in x for both f and g, we seem to get the same thing, but they can't be the same. Notice that if we sub in 0 for x, we get undefined. This is what makes them not equivalent. Now you can say that these two things are the same if you state a restrictions, just stating that g of x is 2x plus 2, but if it was also x cannot equal 0, so it was impossible to sub in 0, that would make the two functions equivalent. G of x equals 2x plus 2 with the restriction x cannot equal 0, and that's the point of today's lesson. G of x, f of x can be simplified by factoring out an x. You could factor out 2x as well, but if you factor out an x, the x's can actually cancel. Now, this is just a little note on rational numbers. Rational numbers are any numbers that can be written as a fraction of two integers. Of course, using number 1 as a denominator also allows us to write any integer as a fraction. So all numbers are rational numbers. Every integer is a rational number. Rational numbers expressions are similar, but we only typically think of rational expressions not as with a variable in the denominator. So if you ever have a variable in the denominator, you have a rational expression, and things can get a little bit interesting. We actually get the shape of things. We've seen the variable if we had 1 over x, and with 1 over x, that resulted in something that we hadn't seen before. It's a shape where we've got like the two lines, as you remember the 1 over x graph, and that was a big surprise for us. So we're just going to start to look at the restrictions. And so this question just talks us through like evaluating the expressions for x equals 2. You can go ahead and do that if you want. I just pause it. I'm just going to talk through them. If you sub in x equals 2 to the first one, you end up getting 2 times 2 minus 3 over 2, 4 minus 3 over 2, which is 1 over 2. That's no problem. When x equals 2, the input is 2, the output is 1/2. The x coordinate of 2, maybe give a y coordinate of 1/2. That's just a coordinate on the graph. No issues there. When x equals 2 for the second one, you plug in 2, you get 2 minus 2 over 2 minus 5. So you get 0 over minus 3. It doesn't really matter what the denominator is, but the numerator is 0. That makes the entire thing 0. Again, this is not an issue. You're allowed to have x equals 2. You're allowed to have a numerator of 0. You just get an output of 0. So if you subbed in x equals 2, you just get an output of 0. And you get a point at 2, 0. The last one's a funny story, though. When you sub in 2, you got 5 times 2, which is 10. 2 minus 2 on the bottom is 0. This is where you end up with a problem. And we call this undefined. Just to be consistent with the rest of the world, this is what we say. The word we use is undefined. It's impossible to divide by 0. You get undefined. And so what happens here is, like, you say that x cannot equal 2 for number c. If you ask yourself, like, what could x not equal for b, you can see that if x equaled 5, that would be a problem. And for a, if x equaled 0, that would be a problem. But certainly x can equal 2 and for these two. But x cannot equal 0 here, and x could not equal 5 here. That'll be the next example. Rational expressions are undefined whenever the denominator is 0. And so it's really important to say what that restriction is. When does it make it undefined? So the question is, like, we're not simplifying yet. We're just looking at when is the expression undefined. And so for the first one, we notice that what value for b can we not have? And so we say, well, b can equal 0 because the top can be 0, but the bottom can't be 0. So b can't equal -2. For the second one, you look at it, and you might take a look at it for a while, and you notice that there's actually no problem here for any value of a, because we're squaring it. The negative values, we're squaring them to become positive, and we're shifting them up 1. This will actually never be 0, and so there are no restrictions in this one. That's a funny one. And then the last one, you might take some time to actually look at this one and plug in numbers. And I applaud you if you can figure out the two numbers that x can't be. But it becomes very difficult to do it in this form. So we ask ourselves, because this is very similar to finding the zeros in a quadratic. And so we ask ourselves, what form is ideal to find zeros in a quadratic? And to find out what values give us 0. And so we think, like, this, if this is standard form, we'd actually prefer factored form. And so that requires you actually to factor this. And when you factor it, you get x plus 6 and x plus 3. And so then it's actually easier to find the restrictions. They come from the two denominators, which is x equals -6 and x cannot equal -3. And so those are your two restrictions. I don't get too comfortable with the fact that, like, just the sign is changing here. If this was like 2x plus 3, we'd have to solve that little equation. So you can imagine, like, you might even want to write that down. Like, if you have 2x plus 3 cannot equal 0, then that would be x cannot equal -3 halves, or -1.5. So you still have to ask yourself, what values for x will make this 0? It's helpful to see those values actually in there and actually making that bracket 0. Okay, but you do need factored form to actually determine that, because, like, it's each one of those numbers. When you multiply them, if either one of those numbers is 0, then you have 0. Okay. I want to kind of go back to this illustration, though. I talked about numbers, and this is a big idea in this unit. The same rules that apply with numbers also apply with expressions. That really is helpful, because we actually can understand the fact that if you can't do it with numbers, you can't do it with algebra. If you can do it with numbers, you can do it with algebra. And so what we're going to do is simplify fractions. That's what we're about to start to do. But I want to start by looking at a regular fraction. Now this is not a grade 11 question. This is an elementary school type question to simplify this to lowest terms. And often you probably wouldn't have a calculator to actually do this. Your teacher would make you to figure it out without a calculator. But we're going to go through the exercise just to relate it to what we're actually going to do with algebra. And so what you might do is actually find out find out what goes into the top and the bottom, and then divide that out on the top and the bottom. And so after some like tedious work, you might realize, and you don't have to get to this right away, but you might realize that 24 goes in the top and the bottom, the top 3 times, the bottom 2 times. So the way I actually wrote it is actually equivalent. Remember that we got the equal sign here. 3 times 24 is 72, 2 times 24 is 48. You might not have written it like this in elementary school. In fact, you probably didn't. But this is what we're doing, is we're factoring. Remember that factoring isn't an idea reserved for quadratics, and it's not an idea reserved for finding the x-intercepts. Factoring is an idea reserved for numbers. It's taking a number and writing it as a product of 2 other numbers. So factoring is something that we do in the grade, like in elementary school, we did factoring. And so what that enables us to do now is to cancel out the 24s, and we're left with 3 over 2. And that's in simplest form. That would be called our lowest term fraction. It's a little bit easier to understand than 72 over 48. And so that's exactly what we're going to do with algebra. So we got some examples here. I made a mistake, and that's why these lines are here, and you'll see what the mistake was. It's kind of funny. Like what you have to do here, and we're going to talk about this more later, is some people are tempted to cancel out the 12 and the 36. Like if you want to see simplify, they just say, let's get rid of that 12 and write 36 as a 3, and then see what happens. That's illegal. You can't do that. It's called illegal canceling. If you put down the numbers like 5 minus 1 over 4 minus 1, you notice that you can't cancel with the ones. Like if you can't do it with numbers, you can't do it with algebra. So what you actually have to do is factor. You can't avoid factoring. Just what we did, we got to figure out what goes into the top and the bottom if we want to reduce these fractions. And so it's kind of actually nice because we don't have to deal with number sense. We just got to deal with algebra. And so, like, really, it's almost easier than factoring 72 over 46 or whatever that last number was. So I want to ask you, is this a complex trinomial? Because complex trinomials are a little bit trickier to factor than simple trinomials, but if it's not a complex trinomial, it's helpful as well. And so actually look at this, and if you don't get this, then your life will be a little bit more difficult. But there's a common 2 in the top. There's a common 2 in the bottom as well, but if you recognize the common 2 in the top, your life is easier for factoring that trinomial. Now the common 2 makes that x squared minus 3x minus 18. And the common 2 in the bottom, when you take it out, makes 2 bracket x minus 6. That way, when we factor the trinomial here, we're dealing with a simple trinomial, not a complex trinomial. Now, you can cheat. I always tell people this, like, when you're actually trying to factor the second part, we're going to leave the 2 alone for a second. But if you factor the second part, we actually probably anticipate that if I'm asked to put this in lowest terms, and this is a quadratic, then I'm going to make a hypothesis that one of those factors is x minus 6. And after you think about it, 2 numbers that multiply to 18 and add to negative 3, minus 6 can be one of them if the other one was plus 3. There was my mistake. I put a minus 3. So you can see the little line kind of cover that mistake up. And I just call attention to it anyway. So you can see that, and now you can always check it to make sure it worked. X times x squared, negative 6x plus 3x, negative 3x, negative 6 times plus 3 is negative 18. So we've got something now that cancels out, or that can be canceled out, and we can say that, all right, let's cancel out the x minus 3, x minus 6's, and the 2's. We get x plus 3. Now, like, we're actually saying equal here, and so what we're saying when we say equal here is we're saying the top line actually equals the bottom line. But going back to the warm-up, that's not entirely true. You might be very surprised to see that top line is actually a line with a y-intercept of 3 and a slope of 1. You know, we don't have to graph that, but that's what it looks like, y-intercept of 3 and slope of 1. You might be surprised to say that, but it's not quite true. It is going to be that in shape, but since the x minus 6's are there, we do have a restriction in the denominator saying that x cannot equal 6. And we have to make that clear. This is going to be a line. It's just there's going to be a little hole at x equals 6 where the graph is undefined. So we simply just say to actually get equivalence, we have to make sure we state x cannot equal 6. The next one we're actually going to look at a little bit different because it's not trinomials or binomials, it's two monomials. So we can actually factor it, and you might try to simplify it right away. But one thing I find that's very helpful is to factor it just like we did the number question. And it looks like this when we factor it. Now that might not be intuitive for you, but x squared is x times x. 12 is 3 times 4, and 15 is 3 times 5. Writing it like this actually shows you what you can cancel out. We can cancel out 2 3's, we can cancel out the x's. And so we end up with 4x over 5. It's not quite 4x over 5. We do have a restriction. We ask ourselves, what can x not be anywhere in the question? And x cannot equal 0. You might say, well, x can't equal 0 on the bottom. But if you look at the top, x cannot equal 0. And if these things are going to be equivalent, then they have to have the same restriction as well. And so since anywhere in the question you're equivalent, and anywhere in the question you have that restriction x cannot equal 0, the whole answer, you have to have that restriction as well. X cannot equal 0. So to maintain equivalence, you need the restriction. The last one, we factor the top and the bottom. We see that maybe the bottom is easier to factor. In fact, people do have trouble with difference squares, but I do see it as an easier factoring method. We know that the middle term cancels out, so the two brackets have to be identical, except one has to be a minus and one has to be a plus. So the bottom is going to factor at x minus 6, x plus 6. And we anticipate when we factor the top that we're going to either have an x minus 6 or an x plus 6. It's impossible to have plus 6 in this case. And so it's got to be x minus 6, x plus 1. That's a tricky one to factor because two numbers that multiply to 6 are 3 and 2. And they add to 5 as well. But there's no way you're going to be able to put the signs of 3 and 2 to get negative 5 and negative 6 when we expand it. And so we actually need negative 6 and positive 1 to get negative 6x plus 1x gives me negative 5x, and negative 6 times positive 1 gives me negative 6. At this point, the x minus 6's can cancel out, and we're left with x plus 1 times x plus 6. We still do have restrictions, and this is probably not the best place to find the restrictions. It's the fully factored form. The second line is the best place to find the restrictions. You might find them here, but it's just a little bit trickier to find them. For example, up here you might identify x cannot equal 6, but definitely here it's a lot more obvious. Here you might identify that x cannot equal plus or minus 6, but on this line it's a little bit more obvious. Here x cannot equal 6, here x cannot equal negative 6. We just state the restriction, x cannot equal plus or minus 6. You don't have to write it like this. You can write two of them, plus 6 and comma minus 6, but it's just a little bit nicer. Two more. We factor the top here. You notice that a 2x will come out, and we got x minus 5. And then we're left with 3x on the bottom. That can't be factored. It's already done. 2's and 3's can't cancel, but the x's can, and so we just leave it like that. And stating the restriction that x cannot equal 0. The last one, it's always helpful when it looks like this. We saw this in the last lesson, but when it looks like this, it's actually helpful if you look at it in decreasing order. So your Pascal's triangle order, the order where x comes first, then the constant, x squared, x, then the constant. This is not in the right order. It's the constant, then the x term. And so what I'm going to do is actually just rewrite the order. And it kind of helps things a little bit. Because in that order, we actually understand that if you ever have a leading coefficient of a negative, we actually want to take that negative out. It just helps for factoring. And so this is the best strategy to take at seeing this question. If you take the negative out, what happens is the signs change. So we've got positive x and minus 2. And that's exactly what we have on the top. So now the x minus 2's cancel out, and we're left with 1 and 1. When you cancel out the top and the bottom, you are left with 1. You're not left with 0. Like, realize that you're dividing here, and whenever you divide by the same thing, you have 1. So the answer there is 1. Oh, you just recognize that the answer is a negative 1 because there's a negative sign. It's not quite negative 1. It looks, that's kind of funny that this is always equal to negative 1. It doesn't look like that originally, but it is a horizontal line at negative 1, except for the fact that x cannot equal 2. Okay. So we ask ourselves again, just to review, and I've already mentioned this, why is restriction necessary to simplify an expression? We'll talk about this more in the next lesson. We just look at, for e, for example, the function equals negative 1 for all values of x. So at any value of x you plug in, you actually get negative 1. It's not quite the same as the horizontal line, though, because like the horizontal line, it just is a line that goes forever through x equals negative 1, or y equals negative 1. So x cannot equal 2. The restriction is important to note to say that the function is equal to negative 1. So the top line is equal to negative 1 with the restriction. It's not equal to negative 1 without the restriction. We have to state that it has a restriction. I said this before, that like if you were to sub this in, like a computer would actually be able to say that x cannot equal 2, but if you were to sub this guy in, you have to tell it that x cannot equal 2. And so, like, if you leave that restriction out, you don't have the whole story. You've got to paint the whole picture. In this last example, I really just want to look at a common mistake. So a student simplifies an expression by doing the following. I just made up this question, but certainly I've seen this. And so what they actually did was they took out the negative 2's right away. And so we just want to show that the function is not equivalent. And so if you sub in, so we actually look at this and we see the student canceled the negative 2 on the top and the bottom illegally. If you plug numbers in there, 5 minus 2 and 3 minus 2, you can't just cancel out the 2's and be gone with them. It's not the same thing. It doesn't work for numbers. It doesn't work for algebra. You have to factor. This isn't the best question because this guy actually doesn't reduce at all. Like, there's nothing to be done in this question. But you can notice that, like, they're saying that the restriction is x cannot equal 0 right here, x cannot equal 2 right here. But absolutely x can equal 0 on the top line. So there's actually an issue there for a couple of reasons. If you cancel the 2 and the 2 and just call them 1s, that's also a problem too. But if you want to verify if something's equivalent or not, we just sub in numbers. If we could show that it's not equivalent, all we have to do is sub in numbers. So if we sub in the top line, I sub in 3. Subbing in 1 doesn't actually prove the point. Subbing in 0 and 2, they said it was already impossible. So I sub in 3, and I get 7 on the top, and on the bottom you just get 3. If you sub in 3, the output's 3. And these are not the same thing. That's kind of blocked there. From that little slide thing, but these are not the same, so it's not equivalent. It's not possible to do that, and actually, like, that's a critical mistake, and you're missing the point of the lesson. You're missing the point of factoring. You can't get around factoring in these examples. Notice that you factor everywhere. Factor. We factored at a negative. We factor everywhere in every question. We factor the top and the bottom. We factor out these numbers. We factor the top and the bottom here. You have to factor. Like, that's going to be a big part of simplifying rational expressions. Okay, that's all for today's lesson.